Very good morning and welcome to this course on the foundations of continuum mechanics. Today we'll be talking about the topics on isotropy and invariance. So let's get started. We will build on the tensor transformation ideas that we have learned in this week and develop the understanding of these two very important terms called isotropy and invariance in the context of tensor algebra and calculus. So let us start this lecture with a question. So the question is that what happens if we apply a rotational transform to delta ij, that is Kronecker delta. And in fact, we will generalize it to an orthogonal transformation. Although in this course, as we said, that we are interested in rotational transformations, so we will use those transformations, but the question is more general as to what happens if we apply an orthogonal transformation to the Kronecker delta, delta ij. So by this question, what I mean is that as we learned in tensor transformation, that if you have a tensor defined in the base coordinate system and we rotate the coordinate system to get the red or the primed or the transformed coordinate system, what will be the component of this tensor in that rotated coordinate system? So let us draw the coordinate system. So here we have a base that is a black OX1, X2, X3 and the primed or the rotated, the red one, that is OX1 prime, X2 prime and X3 prime coordinate systems. So if you remember that we quantify this rotation of the coordinate system using the transformation matrix A, which basically has 9 components, small aij's, which basically contain the information about the 9 rotation angles, that is theta ij's. So our job right now is to find what the Kronecker delta delta ij will become if we try to look at it or if we try to present it in the rotated coordinate system. So delta ij's definition says that it is equal to 1 if the indices I and j are equal, that is the diagonal terms, and it's equal to 0 if I is not equal to j. Now recall from the last lecture that if you rotate your coordinate system, in most cases the components of the quantity will change. Think of a vector. If you have a vector in the base coordinate system and you rotate the coordinate system, the components of the vector in most cases will change. So that what it means is if you try to look at the vector from a rotated coordinate system, the components of the vector will be different. And the same holds for tensors as well. Second order tensors, which have 9 components, will most probably have different 9 components if you look at it from a rotated coordinate system. Also, the 9 new components of sigma prime will depend on the amount of rotation, or it depends on the transformation matrix A that you have. So let us see how delta or Kronecker delta, delta ij, behaves in response to a coordinate transformation, particularly coordinate rotation. So we have a delta ij in the base coordinate system, and when we rotate the coordinate system or transform it, we will get some new components. We'll call these delta ij prime, which we have to find. So for this purpose, we can apply the tensor transformation rule. So the tensor transformation rule allows us to find delta prime given the delta. That is, it helps us find the 9 new components of the tensor given the amount of rotation and the initial tensor. So using the tensor transformation rule, delta ij primes are given as AIP, AJQ delta PQ. Now remember that here we are not specifying the rotations as such. All we know, it's an arbitrary rotation. So the transformation is orthogonal. It's a rotation transform, but the amount of rotation is something that we have not specified. So we'll keep it general for now. So we can simplify this further because on the right hand side we have a delta PQ. So we can apply the Kronecker delta substitution property. So this becomes AIP AJP. I will rearrange the indices of the terms slightly for convenience. So I'll write the first one as AIP, but the second one I'll write it as the PJ term of A transpose, because this allows me to see a multiplication between these two matrices. So this is in fact the multiplication between the matrix A, that is a transformation matrix in this case, times A transpose. But we know that this is equal to identity, as we had shown in this week. So we can apply this. So this becomes delta ij. Identity is delta ij. So what we have shown is that delta ij prime is delta ij. That is, the components in the transformed coordinate system are exactly the same as what we started with, that is Kronecker delta. Now this is a very interesting result. Imagine you're looking at a quantity from a rotated coordinate system and it still looks exactly the same. This is beautiful. If you cannot appreciate this interesting result that we have got, try to think in terms of a vector. So we have a vector v, let's say, and you rotate the coordinate system to get OX1 prime, X2 prime, and X3 prime, and the base was OX1, X2, and X3. Now the new components of the vector will be the transformation matrix A times V. So we can see that in this case V prime depends on the transformation matrix A, that is, it depends on the amount of rotation of the coordinate system, and it also depends on the initial vector V. So in most cases we'll expect that this V prime components will be different. In fact, think about it. Can you find, just as we did for Kronecker delta, can you think of a vector which, when transformed through an arbitrary rotation, stays the same? And the answer is there's none. Well, there is a null vector, but that is trivial. So there is no non-zero vector which stays the same under any arbitrary rotational transformation. So let's write it down. So this is an interesting and important idea, that there is no first order tensor whose components stay the same under any arbitrary rotational or more generally orthogonal transformation. But we do have a second order tensor, and that is what we showed just now, that is Kronecker delta. Let me say that again, that delta ij stays the same under an arbitrary coordinate rotation or more generally orthogonal transformation. And this is a beautiful property. This property has a name, and I'm sure you have guessed that by now. This is called isotropy. And we say that Kronecker delta, delta ij, is isotropic or an isotropic quantity. So I'll write it down that there is no first order isotropic tensor We just discussed that there is no vector that stays the same under an arbitrary orthogonal transformation. So this can be written as there is no first order isotropic tensor. We just showed that delta ij is a second order isotropic tensor. In fact, it is the only second order isotropic tensor. And we can also say that any scalar multiple of delta Ej will also be isotropic. That is, if you multiply a scalar to this quantity, that will also satisfy the property of isotropy. And you can check that from the derivation that we just did. We have shown that delta Ej is isotropic, but we haven't shown that it is the only isotropic second order tensor. We'll not do it right now. But through one of the problems, we will show that delta Ij is the only second order isotropic tensor. So that's a problem for later. So before I move on to the next topic, I would want to talk about the motivation behind or the significance of studying the idea of isotropy. So let's think of a material such as wood. If you try to break wood, it is much easier if you do it along the grain. But if you try that perpendicular to the grain, it's much difficult. Although you may be breaking wood at the exact same position P, but depending on the orientation of the cut or the break, the tendency to break changes. So this demonstrates the idea of directional preference. On the other hand, if you have steel, which is manufactured in such a way that its strength, the breaking strength, remains the same irrespective of the direction in which you try to break it. So we say that as opposed to wood, steel is isotropic. That is, it has no directional preference. So this is the idea or the significance of the motivation of studying the isotropic quantities mathematically. So if, hypothetically speaking, this has no real significance here, but if let us say that the breaking strength of steel, wood, or materials like this was quantified using a second order tensor. Now again, this is hypothetical, this is not the case, but let us say this was the case, that mathematically you were using second order tensors to demonstrate or characterize the breaking strength, then delta Ej would characterize the breaking strength of steel, because steel is isotropic in terms of breaking strength. You could have a scalar multiple of that, but it will be some scalar times delta Ej, because that is a mathematically isotropic second order tensor. All right, so let's go to a third order isotropic tensor. So in order 3, epsilon ijk, that is the permutation symbol, is actually a third order isotropic tensor. Now that we're talking about the isotropy of epsilon, we must talk about the idea of proper and improper orthogonal transformations. So I'll briefly touch upon it. So orthogonal transformation can be of two types. One is called proper or proper orthogonal transformation, and the other is called improper orthogonal transformation. Now, proper orthogonal transformations, an example of that is rotations. Let's write it down. And these orthogonal transformations always result in a right-handed coordinate system, given that we started with a right-handed coordinate system. An example of improper orthogonal transformation is reflections. We saw it in the last lecture. through an exercise towards the end that if you have reflection along a particular plane, we noticed that it resulted in a left-handed coordinate system. So such transformations are called improper orthogonal transformations. So these result in a left-handed system. For proper orthogonal transformations, the determinant of the transformation matrix is a 1, whereas for improper ones, it is actually equal to -1. Now, we are not interested in improper orthogonal transformation, so we'll not go deeper into it. But the reason I discussed this at this stage is because epsilon is a third order isotropic tensor only under proper orthogonal transformations. So what that means is that if you were to transform epsilon to get epsilon prime, and the transform was using rotations, then epsilon prime will be equal to epsilon. But if the transformation was through reflections, then epsilon prime and epsilon will not be equal. Now delta ij is isotropic under all transformations, that is proper and improper, but epsilon ij k, that is the permutation symbol, is only isotropic under proper orthogonal transformations. There's a lot we can say about this, but since in this course we are only interested in rotational transformations, we'll not go into details of this. This topic can go in a lot of detail, but we'll stop here and we'll simply mention that epsilon is the only third order isotropic tensor. So I'll mention this, it's the only. And through one of the problems later, we will see how epsilon is a third order isotropic tensor. So we'll not show that today, that will be left for some later problem. Now let's go to fourth order. So we have in fact three of these, that is we have three fourth order isotropic tensors. The first one is delta ij, delta kl. That's an outer product of two deltas, as you can see. The second one is delta ik, delta jl. And the third one is delta il, delta jk. So these are three fourth order isotropic tensors. Now in general, ifCijkl was a fourth order isotropic quantity, we would write that as a linear combination of these three most generally. So we'll say it's A times delta ij delta kl plus a constant B times delta ik delta jl plus a constant C times, that's a small c, delta il delta jk, where A, B and C are constants. We will be discussing about fourth order isotropic tensors later in the course towards the end when we talk about constitutive modeling. So this is required, and that is the reason I've discussed this. We'll not go beyond fourth order for the discussion today. So now that we have talked about isotropy of tensors, that is tensors which do not change as a result of an arbitrary rotational coordinate transformation, let us talk about a related idea that's called invariance. So let's say that sigma ij is a second order tensor and I define a quantity, so let's call it R, as sigma ij times sigma ij. So this in symbolic notation is simply the double vertical dot product of sigma with itself, but we'll keep to the initial notation. So you can see that R is a scalar. because sigma ij has no free index. So the question is, what happens to R under some orthogonal transformation? Now we know that sigma, when you apply an orthogonal transformation, which is quantified using a transformation matrix A, will become sigma prime. And in most cases, the 9 components of sigma prime will be different from sigma, and they'll depend on sigma, of course, and also the transformation that we have applied, that is A. So it depends on the amount of rotation from the base to the primed coordinate axes. So all 9 components may be different in the most general case. So what we're interested in is that we had defined a quantity R, which under the same coordinate transformation A will become R prime, which is basically defined as sigma prime ij times sigma prime ij. So the question is, what does R prime look like? Let's have a look. So R prime is given as sigma prime ij times sigma prime ij, and I can write sigma prime ij in terms of sigma using the forward tensor transformation rule. So this becomes AIP AJQ sigma PQ. So we'll substitute that in this. So this R prime becomes AIP AJQ sigma PQ. That's the first sigma prime ij. And the second sigma prime ij will be AI. Now I need to use different indices. I'll use L and M. So AIL times AJM sigma LM. So now I'll do some rearrangement of the terms. Now remember, I'll want to use the property of orthogonality of the transformation matrices. So here we have an AIP and the index I also appears in AIL. So I'll write them together. Then AJQ and AJM have the same index J. So I'll write them together. And then we'll write the sigmas, sigma PQ, sigma LM. Now, since I is the first index in both A's, so I'll write this as A transpose PI times AIL, and then I'll write this second one as A transpose QJ times AJM. Now you can see that these are simply A transpose A, which is identity, and in the initial notation that is a delta. Let's complete this. So the first expression becomes delta PL and the second becomes delta QM. So I'll retain P and Q and substitute the other indices applying the substitution rule. So this becomes sigma PQ, and then L becomes a P from the first delta and M becomes a Q from the second delta. This is sigma PQ times sigma PQ. And this is R, that is the quantity, the scalar quantity we started with. Now this is again very interesting. So we have shown that R prime is equal to R. Now what is R prime? R prime is sigma prime ij times sigma prime ij, whereas R is sigma ij times sigma ij. Now what is interesting here is that R prime depends on sigma prime, and sigma prime depends on A. So sigma prime was obtained using an A, and sigma was also arbitrary. We had not decided on any particular sigma. So sigma and A both were arbitrary. Still, the quantity R transformed to R prime, which is exactly the same as R. So it did not change. I sometimes find this more interesting than isotropy, because in this case, the sigma is also the initial tensor that we started with is also arbitrary. Even then, the quantity R, which in this case was defined as sigma ij, did not change. And you already may have guessed by now that quantities like these are called invariants. And the property is called the invariance property. So we have discussed two ideas today. One was isotropy and the other was invariance. Of course, for invariance, we showed for only one particular R, that is sigma ij, but other invariants also exist. We'll discuss this in a later week. But today I'll want to clarify the difference between these two quantities, because in many cases, students get confused as to what is the difference between isotropy and invariance. So isotropy is a property applied to tensors. So we say that we have an isotropic tensor. We showed that for delta ij, that's a Kronecker delta, that's a second order isotropic tensor. You apply any orthogonal transformation and you get the same tensor back. So this is isotropy. Whereas in the invariance, you form some scalar or a scalar quantity from any sigma, and you apply any orthogonal transformation and you get the same scalar quantity back. So the major difference is in isotropy, we talk about isotropy of tensors, whereas in invariance, we talk about invariance of quantities or scalar quantities which are formed or synthesized using tensors. Now, invariance is a property which is true for any tensor sigma, whereas isotropy is only true for the particular isotropic tensor we are talking about. Now, in some texts or cases, you would see that the idea of invariance is also used for tensors. That strictly is incorrect, but depending on the context, you will have to take a call. But for our discussion, we will keep the words isotropic for tensors and invariance or invariants for quantities or scalar quantities which are formed using applying contractions on tensors. By the way, invariants are very common in continuum mechanics or mechanics in general. So we will be talking about these or particular invariants in a later lecture. And also through problems, we'll be learning more about showing objects as isotropic objects and objects or scalars as invariants. So before I close the lecture today, let us do a quick concept check. So I mentioned to you today that delta ij delta kl is one of the isotropic fourth order tensors. So in this concept check, please check whether it is indeed the case. So you'll have to apply the tensor transformation to this fourth order tensor and see that through any orthogonal A, you end up getting the same quantity back. That is the definition of isotropy. So thank you, and I will see you in the tutorial next.